Hello everyone, welcome to this lecture on permutation tests for the course Stat 3150 Statistical Computing. The objectives for this lecture are being able to explain the difference between bootstrap and permutation tests, and then being able to apply permutation tests to two sample problems. So we spent a few lectures discussing bootstrap and jackknife, and we did use those resampling approaches to construct confidence intervals for our estimates. And of course, confidence intervals can be used for hypothesis testing. We're very familiar with this. We can check if the null value of the population parameter would be contained in the interval or not. And this allows us to reject or not the null hypothesis based on a certain significance level. Permutation tests are actually a whole family of resampling strategies that can be used specifically for hypothesis testing. And they're generally more powerful than bootstrap in the sense that power will be higher for the same significance level. Okay, let's start with the motivating example. We'll look at the t-test, and we'll use the chick weights or chick WTS dataset, which is available in base R. This dataset contains 71 observations, and each observation contains the weight of a particular chick and the type of feed that was used to feed that chick. So first, we'll visualize the data. Here I'm creating a series of box plots where the continuous variable is the weight of the chicks, and we'll have a different box plot for each type of feed. And so this is what it looks like. And we can see that there's quite a bit of a difference between the distribution of weights for each of the feeds. We can see, for example, that the median, which corresponds to the thick black line, is highest in casein and lowest in horsebean. But for some of the other distributions, it's not very clear if there's a big difference. For example, linseed and soybean look very similar, and it's not clear if the differences are significant or not. So we could test this using a t-test. And so let's do this. So first I'm going to extract the observations, the weight observations for the chicks who were fed with soybean. So that's the first line here on the slide. And then similarly I can extract the weight observations for the chicks who were fed linseed. Okay, and then just to check the length or the number of observations in each vector, we have 14 observations for soybean feed and 12 observations for linseed feed. And again, we're interested in whether different feed leads to differences in weight, specifically for these two types of feed. One way to formalize this into a hypothesis test is to test whether the mean weight is the same for both groups. And this is what we typically do with the t-test. So we have a null hypothesis, H0, which says mu s is equal to mu L, where mu s is the average weight for soybean-fed chicks, and mu L is the average weight for linseed-fed chicks. And then our estimators are simply the sample means for each group, right? We can estimate mu s and mu L using the sample means. And in Stat 1150, or maybe some other courses you've taken, we saw that we can use the t-statistic to perform a t-test for a difference in means. So we'll do this in R. If you remember, we can do this using the t.test function. And by default, the t.test function in R assumes unequal variance. And just for simplification, we're going to assume here that we're making the assumption of equal variance. And so this is why I'm writing t.test of soyvec, linvec, var equals true. And I'm saving the output into the object fit. Now let's look at the output. This is what the output looks like. We get a nice summary and a lot of information, actually. We see it says two sample t-tests at the top. It gives us the t-statistic, which is 1.32. The degrees of freedom, which is 24. And then the p-value, which is about about 0.2. And we also get a 95% confidence interval from -15 to about 70.9. And finally, we get the sample estimates. So the mean of the vector x, which in this case is soyvec, and the mean for the vector y, which in this case is linvec. And those means are respectively 246 and 218. And so from this, we can see that the p-value is greater than a significance level of alpha equals 0.05, and we would not reject the null hypothesis that the differences are equal. That the difference is 0. The means are equal. And this is, of course, also reflected in the fact that the value 0 is contained in the 95% confidence interval. Okay, so that's a summary of what I just described. So overall, we don't have enough evidence to reject the null hypothesis. But it's important to think a little bit about what are the assumptions going into this test. And to do this, it's helpful to recall how actually this test is constructed. And so first we compute the sample means. Here I'm calling them mu hat S and mu hat L. And then because we assume equal variance, we can actually compute a pooled variance estimate. Let's call it theta hat squared. And then the t-statistic itself can now be constructed as the difference in means over the standard error, which is estimated as sigma hat times the square root of 1 over the sample size in one group plus 1 over the sample size in the other group. If the null hypothesis holds, and if the weights are normally distributed with the same variance, that's the key assumption, then the t-statistic follows a t-distribution on ns plus nl minus 2 degrees of freedom. And this is how we can construct a confidence interval, and this is how we can construct or compute a p-value. So those are the assumptions that are built into this test and which allow us to do inference and hypothesis testing. Instead of assuming that they follow a normal distribution, let's do bootstrap and see what happens there. So we're going to fix the number of bootstrap samples at 5,000. B is equal to 5,000. Next, I'm going to extract the subset of the data chick weights that corresponds only to the rows with soybean or linseed as the value for feed. So this is where I'm doing chick weights bracket chick weights $ feed in the vector soybean comma linseed. Then n is going to be my number of rows, so the number of observations. And next I can do the bootstrap resampling. So very similarly to what we've done before, first I'm resampling indices with replacement. Next I'm creating my bootstrap sample data underscore b as data bracket indices comma bracket. Next, I'm extracting the weight values corresponding to soybean and linseed. And here I'm doing this after resampling the data because actually the sample size, the number of soybean fed chicks and the number of linseed fed chicks will change because remember we're sampling with replacement. And then finally I can extract the average difference. So mean soy B minus mean of lin B. And I repeat this B times. And then we can compute a 95% confidence interval using, for example, the normal bootstrap confidence interval. So first I'm computing my test statistic, or my statistic rather, my estimator for the difference in means, which is simply the difference in sample means. Next, I can estimate my standard error by taking the standard deviation of all of the bootstrap differences in means. And finally, we can compute the confidence interval as mu diff plus or minus 1.96 times the standard error estimate. And the confidence interval we get still includes 0. It's minus 12 to 67. It's a bit narrower. So using Bootstrap, we can compute a confidence interval that doesn't rely on the normality assumption. But the question remains, how can we compute a p-value out of this? Well, you could invert confidence intervals, and that's a topic that we'll explore in the practice problems. But in this lecture, we're actually going to focus on a different resampling technique called a permutation test. And so permutation tests are a very large family of resampling methods that can be used to test hypotheses of the following form. So H0 here is going to be f equals g, where f and g are distribution functions of two different samples. So the null hypothesis will be that we have two samples and that they come from the same distribution. So it's a hypothesis on the whole distribution here. So we can see that it's a generalization of the t-test in two ways. First of all, we replace equality of means by equality of distributions. And then second of all, we don't assume the data follows a normal distribution or any distribution at all. We're only assuming that the null hypothesis is only there to assume that the distributions are the same, regardless of what they are. Okay, and so just as a quick aside, this framework also allows us to test for independence. So assume we have two variables x and y, and let's call their distribution functions fx and fy. Those are the marginal distributions. And then assume that we have a joint distribution as well, which we call f of xy. Then independence is equal to the joint distribution being equal to the product of the marginals. And so this way, by testing the equality of those two distributions, the joint and the product of the marginals, we can actually test for independence. And that's another idea we'll explore in the practice problems, but just know that this test for independence can be done using a permutation test. Okay, so what's the main idea of permutation tests? It goes as follows. Let's assume we have a sample x1 to xn from a distribution f, and y1 to ym coming from a distribution g. If the null hypothesis holds that f and g are equal, then all of those observations are actually coming from the same distribution, let's say f. So x1 to xn and y1 to ym are all coming from from f. Furthermore, any permutation of these random variables is also a sample from f of the same size, because we're assuming f and g are the same. And so this gives us a way to generate data under the null hypothesis. Any permutation of the data will give us a sample from the same distribution under the null hypothesis. And so here's the algorithm. Let capital N be the sum of the two sample sizes, and let theta hat be the estimate from the original sample. So maybe that's the difference in means. First, we're going to permute the observations, x1 to xn and y1 to ym, to get a sample. Let's call it z1 to z capital N. Using that sample, we'll compute the estimate theta hat k for little k, which will be a function of the original sample, of the permuted observations. And then we'll repeat this two steps k times. So we permute the observations and recompute the estimate again. At the end, what we have are k, capital K estimates, theta hat k, that are coming from the null distribution. And so we can compute a permutation p-value by counting how many of those permuted estimates are greater than or equal to the value that we observed on the original sample. And then we count that proportion. Here we're just adding a 1 in the numerator and denominator to make sure that we never get exactly 0 for the p-value. But you'll see other textbooks may actually just give us the sum of the indicator functions divided by capital K. It's a choice. Both are valid. Both will converge to the correct p-value. Okay, so the second step here requires a little bit more details. So what would it look like in the case of a two-sample comparisons? Oh, I guess, sorry, before moving to that observation. So first of all, I just want to point out that this procedure is considered approximate because we're not using all possible permutations. If you were to use all permutations, then you would get an exact permutation p-value. But in practice, what we do is we simulate about 1,000 permutations, which will give us a good approximation for alpha equals 0.05. If your alpha is much lower than this, so let's say alpha is 10 to the negative 5, you would want to increase the number of permutations. So that's the first observation. The second observation relates to the second step in our algorithm. So assume that the estimator is the difference of means, like in the motivating example. So to compute the permuted estimate theta hat k, what we want to do is we would compute the sample mean of the first n observations after permutation, and then the sample mean of the remaining m observations, and then take the difference. The idea here is that under the null hypothesis, group membership is meaningless because there should be coming from the same distribution. And so we could pick any n observations and then take the remaining m observations and call the first one x, the second one y. But it's just simpler to do it systematically by taking the first n observations and the last m observations. Okay, third observation. In Bootstrap, it was important to preserve the correlation structure between different variables because we were trying to mimic the idea of generating new samples from the same distribution. With permutation tests, the idea is different. The goal is to break the association in order to mimic the null hypothesis. So that's the main difference between Bootstrap and permutation tests. And keep in mind, permutations are sampling without replacement, whereas Bootstrap was sampling with replacement. Okay, so let's go back to our example and use permutation tests to compute a p-value. So we're going to fix the number of permutations at 1,000, which is a good number, but in the end it's arbitrary, you could change it. Next, we're going to create a vector called combined data, which will be the combination of soyvec and linvec. And then n, capital N, will be the length of that combined data set. So it's the sum of the observations in the first group and the number of observations in the second group. So for permutations, we're going to still use the replicate function. So we're going to replicate the same code block for k times. And in that code block, the first thing we do is we permute the data. So here you can see that I'm using sample capital N. The way that function works is that if you just pass one argument and that argument is an integer, it's going to give us a permutation of the first n integers. So this is what sample n will give us. It's a permutation of the numbers from 1 to capital N. So you can think of it as permuting the indices again. So perm data will be the permutation of combined data. And next, we want to compute our estimate theta hat k. So first, we're going to create this vector called soy perm, which will be the first n observations from perm data. And we're going to say those are allocated to the first group, soybean feed. The remaining observations will be allocated to the second group, linseed feed. And you can see here I'm using perm data, and then I want to start at little n plus 1 and then go all the way to n, capital N. And so this is why I have perm data bracket, and then in parentheses length soyvec plus 1. This will be little n plus 1. And then finally, once I've allocated those two groups, I can take their sample means and take the difference. So I get mean soy perm minus mean lin perm. And again, of course, this is in a replicate function, so I'm replicating this k times. Okay, so next theta hat will be the first estimate, so the original estimate on the data without any permutations. So, and then I want to visualize the permuted values theta hat k. So I'm using a histogram here. 50 refers to the number of bins. And then I'm going to add a vertical line at the value theta. And then LTY equals 2 means it's going to be dashed. And LWD will just make it a little bit wider so that it's easier to see. And this is what we get. And so the values that we see in the histogram corresponds to the permuted values that we got for the estimates. So you can think of those as coming from the sampling distribution under the null hypothesis. And then the vertical bar corresponds to the theta hat value we got on the original data without permutation. And so we would be interested in counting the proportion of theta hat k's that are greater than or equal to theta hat, potentially in absolute value. So first of all, let's look at this in the context of a one-sided test, right? So if I just go back to the previous slide, here we'll count the number of observations that are greater than or equal to theta hat. So the observations in the histogram that are to the right of the vertical line. And you can see here that I'm doing C theta hat comma results. And this will make sure that we get this extra 1 that I was pointing out in the formula for the p-value. Because this will be theta hat, the first observation in that vector will of course be greater than or equal to theta hat. And now we have a vector of length k plus 1, and so you can check that the math actually works out if we take this sample mean this way. And so the one-sided p-value here is about 0.1, so 0.099. We could, of course, compute a two-sided p-value, which is probably what is more common, especially for a difference in means. And we could do this using absolute values. So now I'm taking the absolute value of C theta hat comma results, and I'm comparing it to the absolute value of theta hat. And now you can see that the p-value is about 0.19, which is not quite twice the one-sided p-value, right? Remember, we're not making any assumption about the distribution, so we're not, in particular, not assuming symmetry. And so this is not exactly twice the one-sided p-value. But in any case, the two-sided p-value that we get using permutations is quite similar, again, to what we got from the t-test. Okay, so we used the difference in sample means as the test statistic, but we could have used the t-statistic itself. And so here I'm just repeating the same thing we did earlier. It's very similar. The only difference is the last line, where instead of taking the difference in sample means, I'm using the t.test function and then extracting the t-statistic using $statistic. And so every time we run those permutations, what we get is the t-statistic. This is probably the easiest way of getting it, but of course you could compute it without using the t.test function. You could use it. You could compute it using R code as you wish. Okay. Next, we're going to take t hat, which will be the t-statistic on the original data without permutation, and we'll do the same as before. We're going to visualize the permuted t-statistics and then check where the t hat value falls. And what we get is something similar to what we got earlier. You can see there's a little bit of skew in this histogram. It's not perfectly symmetric. But if we compute the p-values, we get something similar again to what we got without any permutations. So the one-sided p-value is 0.1. The two-sided p-value is about 0.22. And so all of those different approaches gave us similar conclusions, which is good. It means that our analysis, even with the t-test, was robust to the assumptions we made. Okay, so what we've done is we've assumed that the null hypothesis was that the two distributions were equal. But then we used, as a test statistic, we used something that only compares the means. And you could argue that maybe this is not the best test statistic because distributions can be different even if they have the same mean. And of course, distributions that have different means are different distributions, but it's not strict enough to test whether f is equal to g. And so we can use different test statistics and do the same sort of computation. And so to show you just how flexible permutation tests, we're going to repeat what we just did, but with a different test statistic called the Kolmogorov-Smirnov test statistic, which is actually a way to more directly compare the full distributions. And here I'm giving you the test statistic equation. So we're going to call it D, and it's going to be defined as the maximum of the absolute differences between fnzi minus gmzi, where fn and gm are the empirical CDFs, and zi refers to all capital N observations. So in other words, x1 to xn and y1 to ym. And so we're going to so the way to compute this would be compute the empirical CDFs and then plug in all of the observed values and take the differences in absolute value. And D is defined as the maximum absolute difference. And of course, if Fn and Gm were exactly equal, all of those differences would be 0. And so that's the idea. So we would expect a very small value of D for if the data was actually generated from the same distributions. Okay, and then the asymptotic distribution of D is actually known under the null hypothesis, but it's difficult to compute. And so permutation tests are a simple alternative where you don't need to compute the asymptotic distribution. You can more directly get a p-value using permutations. Okay, so here's how you can do this in our data set, in our example. And you can see, of course, this code looks a lot like what we've looked at so far. The only difference is that instead of using the absolute difference in sample means, or sorry, just the difference in sample means, or the t-statistic, the last line here in the code block is ks.test, which performs a Kolmogorov-Smirnov test. And then again, I'm extracting the test statistic using the $. Right? Everything else is the same. And we're replicating this capital K times. Once the permutations are done, I want to compare those permutations to the value we got for the test statistic on the original data. So this is what I'm doing here. D hat is that test statistic. Once again, it's useful to visualize the permuted test statistics and compare it to D hat, which is what we have on the next slide. And now you can see that we want to look at all of the permuted estimators or estimates that are greater than or equal to the vertical line. For this particular test, there's no definite or no real way of defining a two-sided p-value, right? So there's only a one-sided p-value here. We want to look for large values. And so if we compute that one-sided p-value, we get 0.44, which is, again, greater than our significance level of 0.05. And so we don't have enough evidence to reject the null hypothesis of equal distribution in weights. Okay, so that was, let's do a different example just to see what happens for two distributions that are more different. So we'll compare sunflower with linseed feeds. So first I'm going to extract the weights corresponding to chicks fed with sunflower. And you can see now we have 12 observations for each. And then the rest of the computation is the same as before. Now I'm creating this combined data, which is different than the one earlier. Now it's sunvec, linvec, but the rest is the same. I'm permuting the data inside my code block. I'm taking the first n observations and calling them sunflower feed. I'm taking the rest of the observations, calling them linseed feed. And then finally, I'm computing my test statistic using the permuted data. Next, I can take d hat as my statistic on the original data without permutation, visualize the permuted estimates, and compare this to the estimate we got on the original data. And you can see here the weird behavior. This is because there's actually a lot of ties in this particular example. There's a lot of observations that are exactly equal for the weights. And so this is why we get this weird shape for the histograms. But you can see that there's barely any permuted p-values that are greater than or equal to the vertical line. And so if we compute that one-sided p-value as before, you see now that it's much smaller. It's 0.002, which is smaller than our significance level of 0.05, and therefore we would reject the null hypothesis that the weight distribution is different between linseed and sunflower seed. Okay, so this concludes the slides on permutation tests. To conclude, I just wanted to make a few final remarks. First of all, this was the last module on resampling methods, and what we discussed in that module on resampling was the jackknife, the bootstrap, and permutation tests. They're very different, but of course they have similarities. Bootstrap and jackknife, for example, have similar goals. But bootstrap is almost always better because it is theoretically better behaved, and especially when you want to construct confidence intervals, you have a lot more tools in your toolkit that can account for bias and also skewness in the sampling distributions. On the other hand, permutation tests are specifically for hypothesis testing. It's a way to compute p-values without making assumptions about the distribution of the data. Permutation tests are usually more powerful than just looking at bootstrap confidence intervals. And what I mean by this is that the probability of rejecting the null hypothesis when it doesn't hold, in other words, power, is higher when permutation tests than with bootstrap confidence intervals, typically. And then the last remark is that different test statistics will give different results. And Monte Carlo simulations, which we studied before, the module on resampling methods, is a helpful way in understanding when we should choose a given test statistic, right? So you could simulate data, compare a bunch of test statistics, and see which one is more powerful or more robust to outliers or whatever statistical property you want your test statistic to have.